Hello, my name is Shahriari, and this is a lecture in a series of lectures on abstract algebra based on my book, Algebra in Action. The topic of this lecture is symmetries of a square, and as such, this will provide our first example of a finite group, the dihedral group of order 8, a group that we will use quite often in terms of creating examples and counterexamples for group theory. What's our goals for this lecture? First of all, we want to talk about what we mean by symmetries of a square, and what does that have to do with algebra? Can we do algebra with these symmetries? And finally, point out that this is an example of a group. What is a symmetry? We have a square and we label its corners. So, for example, here I've labeled them 1, 2, 3, 4. We want to know what kinds of symmetries this object has. One way to think about it is the object is sitting in a frame exactly the same size as itself. We take it out of its frame, then we do some kind of a movement, move it around, flip it around and so on, and then put it back in the frame. And that final result is called a symmetry of a square. So for example, the one that I've shown here is a 90-degree rotation counterclockwise. We took the square out of its frame, we rotated it 90 degrees counterclockwise and put it back. And that makes it a symmetry of a square. If I said 20-degree rotation, if you take a square and rotate it 20 degrees, then it still will be square, but it won't fit in its frame, and therefore it's not a symmetry of the square. If you had a circle, then you could do a 1-degree rotation or 2-degree rotation or 20-degree rotation, put it back. What I do in the process doesn't really matter. Like if I flip the square several times and then rotate it and so forth, the final result matters. Where did the corners end up? You can think of this as a function on the corners. You are going to send the corners of the square to other corners. Before we list all the symmetries, it makes sense to try to think how many of them are there. There's the rotations. So we did the 90-degree rotation. We can do other kinds of rotations like 180 degrees, or here I have the 270 degrees. Our rotations will always be counterclockwise, just so that we know what we're talking about. We also have flips. For example, this is a vertical flip. You can imagine a vertical axis of symmetry going right down the middle and then flipping your square about that axis. If you take your square and flip it, the place of corners 1 and 2 switch and the corners 3 and 4 switch. I colored the labels on the other side blue so that we know when we're looking at the front side or the back side. Flipping is a reasonable symmetry. Before we list all of them, let's just see how we would count how many of them are there. And the way to do that is to focus on one of the corners. We can do that because the end result matters, not the means, not how we got there, because there's a million different ways to get to one place. For example, a 90-degree rotation clockwise is the same as R270. If you go 270 degrees counterclockwise or 90 degrees clockwise, you've physically done a different thing, but the final result is the same. And as far as we're concerned, those symmetries are the same. To count the number of symmetries, you focus on one of the labels. The corner labeled 1, where can it end up after we're done? Well, there's only 4 corners, so there's 4 choices. There's 4 choices where to put 1. Now, if you put 1, is everything else determined? Yes and no. In some ways, things are determined, but not completely. When you decide where 1 is, 3 will be on the opposite corner. But then 2 and 4, they have 2 choices because you could flip things and flip the place of 2 and 4. When you decide where 1 goes, if 1 goes here, you can flip your square, and that gives you 2 other choices. But as soon as you decide whether or not you're going to look at the front or the back, after having decided where 1 goes, you're done. There's nothing else you can do. If 1 is fixed, so is 3, but you could be looking at the front or the back by flipping the square. And so the total number of symmetries of a square is 8. We can list them, the 8 symmetries. There are the rotations. I put R0, that is also a symmetry, which every geometric object will have. If you take any geometric object out of its frame, you can put it back in right the way you found it. The square has other ones. You can do 90 degrees, 180 degrees, and 270 degrees. All of these are counterclockwise. You can flip it horizontally, so an axis that's a horizontal axis right through the middle, vertically with a vertical axis of symmetry. You can also flip it diagonally. And there's 2 diagonals. You can flip it across the main matrix diagonal. Here I'm keeping 2 and 4 where they are, but switching the place of 1 and 3. I'm looking at the back side now. That's why those are blue. Or you can take the off diagonal, the other diagonal, and flip around that axis. So D is going to be a flip about the main matrix diagonal, and D prime is going to be the other one. And so here there are 8, and we don't have to look for any more because we knew that there was going to be 8. We have a set of elements, and this set of elements we're going to call D8. The 8 is going to stand for how many things there are. That's what algebraics call this set of objects. Topologists tend to call it D4, and they focus on the fact that these were the symmetries of a square, and a square has 4 sides. These are the elements of D8. There's R0, R90, R180, R270. Those are the rotations. And then there are the flips, the horizontal one, the vertical one, and the ones across the 2 diagonals. We want to have an operation on this set. We have something that we're going to call multiplication. It's not multiplication in the sense of 2 times 3 is 6. This is a new multiplication. We want an operation on this set, a binary operation, an operation that you take 2 elements of this set and you get a third one. And we're going to call that a multiplication. And this way of combining them is not rocket science, it's just following one operation by the other. We think of H as doing things, acting on this square. H is flipping the place of 2 and 3 and the place of 1 and 4 because it's a horizontal flip across a horizontal axis of symmetry. And then maybe we follow that by 90-degree rotation. When we flip, we're looking at the backside. And when we do our rotation, we're still looking at the backside. This combination of these 2 things is itself a symmetry because we took the square out of its frame, did 2 things and put it back. It must be one of the ones in the list of 8 that we had. And in fact, if you look at this, this is D prime. If you forget the intermediate step and go directly from where we started to where we ended, what we have done is we have done a flip across the off diagonal. So 1 and 3 are fixed and 2 and 4 are switched. So this is going to be our operation, this following one by the other. The way we're going to write this is we're going to say R90 times H equals D prime. The notation needs a little bit of explanation because why didn't I write HR90 equals D prime? This is the function notation. When we compose 2 functions, we say f of g of x. And even though g is done first, g of x, you apply g to x, then comes f. We write it as f of g of x. We write the second thing first. So this is the function notation. Actually, in algebra, if you look at algebra books, there will be quite a few where algebraists revolt against that and would like to do it the other way around. Because as far as algebra is concerned, there's no advantage really to writing function composition in that way. To say that f circle g means do g first, then f. Might as well do f first, then g. If you switch that, then lots of things change. Instead of f of x, would write parentheses x f, which will sound weird to you. I actually like that other system. I haven't been trained as an algebraist, but a long time ago I decided that, as Leonard Cohen would say, everybody knows the war is over, the good guys lost. So this is one of those cases where I'm going to go with what you're used to. Think of h as a function on the square and R90 as a function on the square, and you're doing R90 of h of the square. As soon as we say multiplication, the question is, does it have the same properties of the usual multiplication of 3 times 4? And one of the things it doesn't have that I want to point out right away is that it's not commutative. 2 times 12 is the same as 12 times 2, but that's not the case with this multiplication. We saw what happens when you do h and R90, you get D prime. But if you do it the other way around, if you do R90 first and then do h, you can see that this time the flip was about the main diagonal axis, and this was D. So H R90 is D. So this composition of symmetries is not commutative. You might say, well, then that shouldn't make it multiplication. No, it does. In fact, this points out that the thing that really needs explanation is why is 2 times 12 equals to 12 times 2? Because actually, when you do operations like this, often things are not commutative. If I want to leave this room, the act of opening the door and leaving is not the same as if I leave and then try to open the door. My nose would not like that. Or if I'm eating a chocolate bar and wrapping that chocolate bar and then eating it is very different than eating it and then trying to unwrap it. So almost all operations are not going to be commutative. And so why is it that 2 people carrying 12 watermelons each is the same as 12 people carrying 2 watermelons each? That's the thing that needs explanation, not why this is not commutative. Now that we have this multiplication, we can make a multiplication table. And so on the rows, we label them with the symmetries, and in the columns. And for example, we'll say R90 times R90 is R180, and we fill that entry in the multiplication table. Or R90H is D prime, H R90 is D. This is not fully completed because I want you to do it. You should actually stop the video, make yourself a square, and do some of these, maybe all of them. But this is an abstract algebra class, and what we would like to do now is to do actually algebra with these symmetries. Now, in high school, when you do algebra, you immediately think of X. You think of a variable, of giving things names, and then appropriately working with them, multiplying things together, adding things, and so forth. Here, we don't have two operations. We don't have addition and multiplication. We just have multiplication, but we still want to do algebra. And so for that, I want to introduce new notation, and I want to give these guys, these symmetries that we have been working and talking about, new names. We'll start with R0. R0 was the most boring symmetry there is, the one that you take the object out of its frame, put it right back in without doing anything. And throughout this course in algebra, we're going to call that E. You could call it 1, for example, because it acts like 1. When you multiply by something, nothing happens. But we're going to keep calling that E. But other than that, I want to also give a name to R90. That was 90-degree rotation counterclockwise. I don't want to keep writing R90. I'm going to call it A. But what should I call R180? Well, maybe I could give it a new name, but I don't have to, because R180 is R90, R90. That's A, and that's A squared. So if R90 is A, then R180 is just A squared, and R270 will be A cubed. Now, what about A to the fourth? Well, if you do one more R90, then you're back to having done nothing. And so A to the fourth is the same as E. And this is one place where high school algebra is different than algebra with the symmetries of the square, because for the symmetries of the square, A to the fourth isn't just A to the fourth, but it's another name for E. And A to the fifth, for example, will be the same as A. A to the sixth will be A squared, and so on. But no matter how many powers of A I find, I'm never going to get a reflection. When you rotate as many times as you like, what you're going to get is rotations. You're never going to get a flip. So I need another name for one of the flips. And I'm going to choose B for H. I could have picked any one of the flips. I'm choosing H to be called B. We will have to be consistent. And within this course, whenever I'm talking about symmetries of the square, H is going to be denoted by B. Then I can do the same thing I did before, which is look at powers of B. What about B times B? Well, B times B, if you do a horizontal flip twice, you're back to where you started. You get B squared is E again. And no matter how many more times you do H's, you're just going to get H and E and H and E and H and E, and you're never going to get anywhere. So what about the other guys? What we can do now is multiply A and B together. Remember, when we write AB, you do the one on the right first. So that means do a horizontal flip and then a 90-degree rotation counterclockwise. And we have seen that what you get is D prime, one of the diagonals. You can also do A squared B, and you should stop the video and try that. And A squared B is going to be V, the vertical one. And finally, A cubed B is going to be D. However, we actually saw that BA is also D. So one other relation we have, BA and A cubed B are the same. That's important because multiplication of these symmetries is not commutative. So BA is not the same as AB. BA is the same as A cubed B. And that'll be very useful because it allows us to move A's past B. If you see a BA, you can take the A and move it to the other side, but at a cost. And the cost is that when you end up on the other side, you're not A anymore, you're A cubed. I can now write my D8 in terms of these A's and B's. The elements of D8, the 8 elements, the 8 symmetries of square are E, A squared, A cubed, B, AB, A squared B, and A cubed B. And then when I write this, I also want to always remind myself what the relations are, because if I just write those elements without the relations, I might think that, well, from these, I can make other ones. I can make A to the fourth, A to the fifth, A to the sixth, B squared, and so forth. I have to remind myself what those relations are. A to the fourth and B squared are both E, and BA is A cubed B. And as we shall see, those relations are going to be enough in the sense that they allow me to reduce any word you write in terms of A's and B to one of these 8. So what good is this? For example, you might ask, what's VH? And what you could do here is take a square out and do a horizontal and then a vertical and see what you get. That's what VH is. Do H first, then V. Again, VH means you start on the right, you do H, and then you do V. But that's a geometric thing that we do. And one of the reasons algebra was powerful was that it allowed humanity to get away from geometry. That's a good thing and maybe not a good thing at the same time. It allowed us to make arguments without having to rely on geometry. Originally, when algebra started, people didn't trust that, and actually all algebraic identities were proved geometrically. But over time, people realized that you can trust algebra. So what's VH? Well, V, I know what it is. V is a squared B. And I know what H is. That's just B. So VH is a squared B, B. But now BB, that's B squared. And so I get a squared B squared. But B squared, that's E. And so that's R180. And so I did that without drawing anything, any squares, and without doing any sort of physical things to find out what VH is. VH is R180. Algebra is already useful. Here's another example. Let's say that you want to know what's R90, H, R90, VD. That means do D first, then V, then an R90, then an H, and an R90. And you want to know at the end of the day what you're going to get. Well, you say that I know what R90 is. That's just A. What's H? Well, that's just B. So you write all of these down. So A for R90, B for H, A for R90. For V, we write A squared B. And for D, we write A cubed B. We have to be careful because unlike high school algebra, you can't just combine like terms because the multiplication is not commutative. You can't just move things over to combine them. You can combine things that are right next to each other. So for example, right here, A and A squared, those are right next to each other. And so they get multiplied and that gives us A cubed. So I'm using associativity of the multiplication there. I could do different kinds of things here. A cubed B is another name for BA. And that's helpful because these two B's are going to be next to each other and A and A cubed are going to be next to each other. And so B times B becomes B squared and A times A cubed becomes A to the fourth. And so I get AB squared A to the fourth B. But what's B squared? That's E. What's A to the fourth? That's E. And multiplying by E doesn't change anything. So what I have is AB, which is D prime. And so again, I was able to do R90, H, R90, VD without any geometry and just using algebra, which is one of the advantages of algebra. By a word, I just mean a string of A's and B's. Every word made with A and B is some symmetry of the square, and we've seen that all symmetries of the square you can make from A and B. Using these relations, you can simplify things. Using A to the fourth equals Z and B squared equals Z, if A's and B's are right next to each other, you combine and you reduce them. Using BA equals A cubed B, you can move an A across B, get A cubed B, you can simplify each word, and all of them are going to be of the form A to the I, B to the J. I can only be 0 or 1, 2, 3, 4. And J can only be 0 or 1. When it's 0, that means it's not there. If both I and J are 0, A to the 0, B to the 0, that's going to be our E. Another way of writing D8 is to use pointy brackets. The way we read that is that D8 is generated by A and B, but with the following relations. A to the fourth equals E equals B squared, and BA is A cubed B. A and B are called the generators of D8. You can have different generators. You could have different relations. The point is that you don't need anything else other than the three that we have because you can reduce every word down to one of our familiar forms. Now I want to talk about what properties does multiplication in D8 have. First of all, we have the closure property. If you have two elements of D8, any one of these symmetries, and you combine them, that combination is also symmetry. We also have the associative property. That means that if you have three elements, three symmetries, and you do them in a row, it doesn't matter which two you combine first. So xy times z is the same as x times yz. And if you think about it, both sides is just saying do z first, then y, then x in terms of symmetries of the square. And if you do z, then y, then x, it doesn't matter if you do z, then y, and then x, or you do z and then y and x. And that's really because function composition is associative. Also, we have this weird element E, which is sort of a boring element, but a very useful element. It's called the identity. And it has the property that when you multiply it by any element, nothing changes. For every element of D8, EX and XE is X. And when you have an identity, it's not like the identity is going to announce that I'm the identity. It might be camouflaged in some way. You will know that it's the identity if when you multiply it by every other element in your set, it doesn't change it. The final property is the existence of inverses. So what does that mean? That means that for every element in D8, every one of the symmetries, we can undo it. If you didn't like H, well, you can do H again, and you're back where you started. If you didn't like R90, then you do R270, and you're back where you started. You're back to E, be back to doing nothing. And so for every element in D8, there's some other element, its friend, or maybe its enemy, that when you multiply X and that element, either way, you get the identity again. again, just like identity, inverses don't come announcing themselves. I'm calling it X inverse as if it's always saying I'm X inverse. No. For example, A inverse is A cubed in V8. H inverse or B inverse is B. So H has the name B, but you could also call it B inverse because when you take H times H or B times B, you get identity. These properties make D8 a group. So a group is a set together with an operation. We don't know what the elements of the set are. Here we do. They are symmetries of a square. And usually we don't know what the operation is. Here we do. It's combining the symmetries. A set together with an operation that has these four puny properties: closure, associativity, the existence of identity, and existence of inverses. Then we have a group. And group theory is the study of groups in abstract, not studying just D8 in particular, but studying groups in general. And the hope is that, first of all, other than D8, there's a lot of other groups. And yes, there are, for example, instead of a square, you can take any other object, symmetric or not, and find its symmetries. And those symmetries will form a group because they will have exactly the same properties, but there will be tons of other ones. And future lectures will go through 3 other sets of examples before we start formal study of groups. The purpose of those examples to show that there's many times when we have a set together with an operation that satisfies these 4 things. If we can prove things about groups in general, then they apply to all of these situations all at once, and there will be much efficiency in doing that. You should reserve judgment in terms of whether or not you agree that this is worth studying because of the following. All I'm saying is that when we're going to study groups, all we know is that we have a set and an operation. We don't know what the elements are. We don't know what the operation is, and it satisfies these properties. And your question could be, okay, fine. And that applies to lots of other things. I agree with that. But how do I know that anything profound can be said? How do I know that starting from these sort of almost silly axioms, you can actually get anything, like you can say anything about groups? And that will be the purpose of this whole set of lectures, to convince you that that's the case. This is called algebra, and we can actually do algebra with these symmetries. For example, an algebra question usually is find x. Find x that satisfies a certain property. Someone might ask you, find x if what you know is BAXBA equals A squared. Now, A and B, what are they? Oh, they are the elements of D8. A is R90 and B is H. But I want to know what symmetry can I find so that if I do A, then B, then X, then A, then B, then I get A squared. And remember, when I'm saying which one I do first, I start from the right. And that because this is function composition, if you're thinking of it as symmetries and doing things to the square, you're starting from the right. You could do this with your square and try to figure out what X is. But now we can do algebra. And how do we do that? We do the same kind of thing we do in high school algebra. We try to isolate x. In high school algebra, you say if it's 3x equals 5, you multiply by 1/3. We multiply by the inverse of the elements, but it's important which side because things are not commutative. The first thing I'm going to do is I'm going to get rid of that a on the extreme right of the left-hand side, and I do that by multiplying both sides of the equation by a cubed. If BAXBA equals a squared, then BAXBA times a cubed should be the same as a squared times a cubed. And the reason I multiplied by a cubed on the right was that a times a cubed on the left-hand side becomes e. And on the right, I get a squared times a cubed. Well, that's a to the 5th. Why is it a to the 5th? Well, because a squared is a cubed is a, and so there are 5 of them. And a to the 5th is a. Why? Because a to the 4th is e. And when you do it one more time, you're back to a. The equation has now simplified to BAXB equals a. Now I want to get rid of one of those b's. So multiply on the right both sides of the equation by b, and the b's cancel because b squared is e. And on the right-hand side, we have AB. Now I've got to work on the left, get rid of the B and the A on the left. So I first multiply by B, not by the inverse of A, because the inverse of A would not be able to get to A. You first have to get rid of that B, peel that B off. So multiply by the inverse of B, which is B. And on the left, you get AX. On the right-hand side, you get BAB. But BA is A cubed B. And I have A cubed BB. And b times b is e, so I get a cubed. So far, I have ax equals a cubed. And so x is a squared, x is 180-degree rotation. This is the end of this lecture. This was an example of a group, D8, a group that we will see often in the course of these lectures.